Okay, a quick overview of the logistic function we started with. So dp dt equals 3p minus p squared over 6,000. Now we factored out a p over 6,000 and we got that it was p over 6,000 times 18,000 minus p. And we know this is logistic, so our carrying capacity is L of 18,000. So we did our first derivative, discovered it was positive before 18,000, negative after 18,000. Our second derivative was positive from 0 to 9,000, negative from 9,000 to 18,000, and then positive from 18,000 to infinity. Now these are populations. This is our population, not the time that we're talking about. But when our population is 20,000, I know that our function will actually be, our population function will be concave up, and it will be decreasing. So I have three different starting populations. I have a starting population of 4,000, a starting population of 10,000, and a starting population of 20,000. If I was asked in these three scenarios, what is the limit as t approaches infinity of our population function itself, I do not have to know what the population function is to do that. You can actually take the limit as t approaches infinity of that, but I know that our carrying capacity is 18,000. And I know that our function will always approach our carrying capacity, so no matter what our starting population is, the answer will be 18,000. That's one nice thing about logistic functions. You know where it's headed in the long term as time goes by. Now the range of the solution curve. So if I start at a population at 4,000, I know that it's going to go up to 18,000, but it is going to level off at 18,000. It's going to approach our carrying capacity. So I'm going to say our solution curve does have a starting population of 4,000 and is going to end at 18,000, but not actually touch it. If we started at 10,000, it's still below our carrying capacity, so it's going to look very similar. I'm going to start at 10,000. And I'm going to approach 18,000. Now if our carrying capacity is 18,000 and I start above it, then I know that I'm going to be approaching the 18,000, but I'm not going to reach it. But 18,000 is the smaller number, so it'll come first, up to 20,000. So those are the intervals in which my population curve will actually be. Now, when is it increasing and decreasing? If I start at a population of 4,000, since I'm only going up to 18,000, it will be increasing the whole time. So I will say from 4,000 to 18,000. And if I have to justify that, I'd say it's because dp dt is greater than 0, and it does not decrease. The same holds true if I start at 10,000. So I would say from 10,000 to 18,000 and dp dt is greater than 0. So we are increasing on this interval or increasing on this interval. Now if I start above the carrying capacity, I'm going to decrease towards the carrying capacity, so from 18,000 to 20,000. And my dp dt is less than 0. Now for concave up, concave down, you can see that concavity changes right here, and we would say concavity changes here, but you're not going to have a solution curve go through this at any point. So 9,000 is our point of inflection. So if you start below 9,000, like our first scenario, it's going to start concave up and then change to concave down at 9,000. So for up, I have from 4,000 to 9,000, and then for down I have from 9,000 to 18,000. And I'm looking when my second derivative is positive, my second derivative is negative. Now for the next scenario, I started above my point of inflection. I started at 10,000. So it will actually be concave down the whole time. So down from 10,000 to 18,000, sorry. And if I was asked to justify it, I would say my second derivative with respect to time was less than 0. For this one, more than 0, less than 0. If I start above my carrying capacity, my graph is going to head down towards the carrying capacity, and it will be concave up while it does it. So I will say up from 18,000 to 20,000. And then I could say, if I was justifying, my second derivative with respect to time is greater than 0. So all of these, for a sketch of all of these graphs, the important numbers are 18,000, and I can mark a 9,000 if I like. You always want to know what the important numbers are in logistic, and it's the carrying capacity and the point of inflection if it exists on your graph. So for this first one, I'm starting in a population of 4,000. So down here, this is about 9,000, so 4,000. It's going to be increasing and concave up. It's going to change to increase and concave down and flatten out. And that would be the sketch of my graph. If I start at 10,000, it's going to be increasing the whole time up to 18,000, but it will be concave down. So it's flattening out. If I start above 18,000, it will be decreasing but concave up. It's headed towards my carrying capacity. Now it's important to note that for the logistic functions, right here at the point of inflection, that is when the population is growing the fastest. You can see the curve getting steeper and steeper and steeper, and then it becomes shallower and shallower and shallower. So it is always growing fastest at your point of inflection. And that's just a quick summary of what you can tell from the first and second derivatives of a logistic function.